The first talk is given by Dr. Taylor Groves, who is a principal solutions architect at Lightmatter with a focus on distributed systems architecture, performance modeling, and high-performance interconnects. Previously, he worked as an architecture and performance researcher at Berkeley National Labs and Sandia Labs, where he architected the Perlmutter system and helped define the upcoming Dundas system. He has over 35 publications focused on system architecture and performance. He holds a PhD in computer science from the University of New Mexico and a BS in computer science from Texas State. Taylor?
Hi there. Let's see. Get this sharing. Thanks for that introduction. I appreciate it. And really thrilled to be here today. So I'm a solutions architect at Lightmatter, and I'm going to be talking about how we can accelerate frontier mixture of expert training with 3D integrated optics today. So while I'm presenting this work, it was definitely done as part of a team, and I want to acknowledge those authors here. Hopefully they're in Slack as well. So if we have questions that are outside of my expertise, they'll be able to help you out there as well. Yeah. Okay, so I'm going to talk about Passage, and Passage is and also I want to close out some of the Zoom stuff. There we go. Passage is a solution to AI scaling. So it's really a 3D stack of photonics, electronics that integrates massive bandwidth, low power, and it does this beyond copper reach. And so what you're going to see in this work is an 8x increase to scale up pod bandwidth using half the energy of conventional CPO. We're also going to show a 6x reduction in package area expansion compared to CPO and a 2.7x increase to MoE training throughput. We're going to begin with a little bit of motivation first, though. So AI is continuing to scale. As Amin pointed out today, there's really unlimited appetite for increasing hardware to meet the exponential growth of these model sizes and training workloads. We can't provide enough flops, memory bandwidth, or network. AI scaling in particular is needing extensive use of the network for GPU to GPU parallelism. So this is tensor, expert, context, pipeline, and data parallelism, as long as whatever else gets invented next. You also have GPU to IO communication. So this could be checkpointing, context caching, and prefill. And then we have chain of thoughts and reasoning models coming along. All of this has led to the scale-up pod, which is really the unit of compute now. It's not just a single GPU package. The reason for this is that process improvement alone is not enough. You're getting about 15% improvement gen on gen from TSMC or anybody else. And if you really want to continue to provide the scaling that AI requires, you have to, target some other vectors. And what they've done in the past, if you compare Volta to Rubin, is you've increased the package size, 2.3x. You're doing this to increase the number of logic and memory dies per package. This is what's enabling you to get more HBM bandwidth generation on generation, as well as the increase in frequency and other things like that. You're increasing power as well. So this is 5x increase at both the package and pod level. And then finally, you're increasing the pod size. And when I'm talking about pod, I'm talking about a scale-up pod, scale-up network that really take a number of accelerators, tightly couple those with high bandwidth and low latency. And so we're seeing a 4.5x increase in the number of packages per pod, the number of GPUs that we can support, and a 12x increase in the scale-up bandwidth per GPU. So this is all contributing to greater performance for AI, but these conventional technologies have also hit a wall, and I'm going to talk a bit about that. The first challenge is that the package area and shoreline are not really able to provide what IO needs. So if you look at, going from one generation of GPU to another, in the first generation, you might have 2 logic dies with 8 HBM packages. As we go to the next generation, we're going to go to 4 logic dies. We're going to 16 HBM dies. And this is going to enable you to have twice as much HBM, twice as much logic. But if you look, your IO is not growing at all. The available shoreline stays the same. And This is because communication happens at the chip perimeter. There's simply not enough shoreline, and it makes it so that we're in this paradigm where you're reliant on the SerDes speed to increase in order to get more bandwidth, or the SerDes to become smaller. A second challenge is the scale-up challenge. It's how do we get the full GPU bandwidth to as many GPUs as possible in nanoseconds? And I want to contrast for a moment the scale-up network with the scale-out network. Your scale-up network is going to be, maybe 1,000 GPUs. Your scale-out network could go to 100K, a million GPUs. In terms of latency, you're talking 100 to 250 nanoseconds for your scale-up network versus 2 to 10 microseconds for scale-out. In terms of bandwidth, your scale-up network is going to be tens of terabits per second at a starting point. It can go much higher. Your bandwidth on the scale-out network is 1.6 terabit per second. And so this also translates to energy. The energy for a scale-up network needs to be less than 5 picojoule per bit because you're sending so much data off of the GPU, in contrast to a scale-out network where it might be 16 picojoule per bit. These performance requirements have led to the selection of really just a few topologies that we're seeing today. So I'm going to be talking about the multi-rail single layer of switching. And what this is we want every GPU in the scale-up pod to be able to connect to any other GPU at full bandwidth with one switch hop. And so what happens is you have a switch that has to have the number of ports equal to the GPUs it's supporting. It has to be connected to every single GPU in that topology. One switch is not going to be able to provide enough bandwidth for all of these GPUs. So then you end up doing multi-rail where you're shotgunning the data up from the one GPU across all the switches and then back down to another GPU to get the full bandwidth. And what this has led to is challenges around copper reach and pod density. So if you look, the problem is that you're trying to connect every single GPU to every single switch with copper. And if you consider that the copper reach today at 224 gig is about a meter, you're extremely limited in the ways you can configure this. You're having to have very dense racks. And I like this quote from NVIDIA below where they say, NVIDIA is leading the transition to 800 VDC data center power infrastructure to support megawatt IT racks and beyond. I'm not sure that's where we really want to go, but this is the state of things. And if you go to 448, it only gets worse. You're, at a half a meter or so. So now I want to provide a little bit of a primer on Passage and how Passage can solve these different challenges. So Passage is really this bullet 2 in the middle here, but it's helpful to view it in the context of the entire chip, right? So bullet 1 is your EIC. This is your SerDes. And I want to note that the SerDes now are spread throughout the entire area of the EIC. We're no longer limited to the shoreline with Passage. And why is that? It's because those SerDes can tunnel vertically down and undergo the electrical to optical conversion directly beneath them. So Passage is this combination of waveguides and TSVs and modulators and optical elements that sit right underneath that. The optical signal, once it's in Passage, goes through these waveguides routes. It can go to another chip on the package, or it can go out via a fiber attach unit in the fibers, bullets 3 and 4. All of this sits on a substrate. So let's take a look at this from a 3D cut or from a cut through view. So in bullet 1 here, we have SerDes. If you look, they're completely spread out throughout the entire EIC on top. These can be low power SerDes compared to what you're traditionally seeing. And the reason for that is that we have less than 100 micron between the electrical EIC and the PIC, so that your electrical channel is going over the shortest possible distance before getting converted to optics. It allows us to use things like XSR SerDes and save a lot of power. Once you arrive at the PIC, you go through a driver to a microring modulator, and these microring modulators allow for wavelength division multiplexing. So this is multiple TX and RX on the same waveguide and fiber. We just announced 16 lambda bidirectional, which is state of the art. Once you're in this waveguide network, we have these waveguides are incredibly small, about 4 micron. They're routing throughout the PIC. There's optical circuit switching to control where you go, whether it's across a reticle using waveguide stitching or to a fiber attach unit. These fiber attach units are pluggable, enabling high volume manufacturing. And the fibers themselves are incredibly small. So we're talking 127 micron, and it allows for incredible bandwidth density that completely eliminates these SerDes shoreline problem that we saw before. Because it's optics, you're extending the reach of the scale-up network to hundreds of meters. And then lastly, in bullet 7, we have TSVs that provide power and signal through the EIC to the chip on top. So just to summarize how Passage solves these different problems that I outlined before. We solve the bandwidth density and radix problem. We have over 896 gigabits per second per fiber, 16 lambda. We're doing bidirectional TX and RX on the same fiber. So this doubles your port count instantly. You have greater than 4 fibers per millimeter for extreme bandwidth density on the shoreline. And you can see this is 114 terabits per second demonstrated on package. You can check out our hot chips presentation, I think early next week. As far as data center reach goes, there's thousands of XPUs now enabled in a single scale-up domain, and they don't have to be within 1 or 2 racks. So you're alleviating all those rack and cooling and power challenges. Lastly, the 3 stacking and power efficiency is absolutely state of the art. So we have 100 micron between the electrical and optical conversion, allowing you to use these energy efficient SerDes. We're showing power delivery at greater than 1500 watts, and the silicon photonics and lasers are 2.3 picojoule per bit. Because this is 3D stacked, we have minimal package growth as well. So if we wanted to explore what this looks like for a 32T GPU in the future, looking at different optics technologies and how you build that, we're going to show that now. So you have 80 ports at 400 gigabits per second. If you look at one of the conventional approaches, you might be thinking of LPO, linear pluggable optics. So if you have a 4,500 square millimeter GPU, these LPOs are going to provide you about 13 picojoule per bit when you include the host SerDes. The reason for that is you still need, even though you're using LPO, you still need a pretty beefy SerDes on the GPU or the switch to be able to send a quality signal across these copper traces or even co-packaged copper. The modules themselves are 2,300 square millimeters for the extra dense modules, and you need about 10 of them. So it's a massive area that you're having to add on the board to support the bandwidth off of this GPU. The copper that you're putting on there is not easy to deal with as well. There's incredible mechanical stress, reduced airflow, and a lot of challenges around that. The second option could be 2D CPO. So if you look at this, you're having an optical engine that's on the substrate, and then you're taking those electrical traces through the substrate and up to it. So this requires some beachfront expansion. And when you look at that, let's say you have 1.7 terabits per second per millimeter bidirectional bandwidth out of that optical engine. That's going to result in about 470 square millimeters of growth, not including your beachfront and substrate growth. So you're going to more than double your package area in this case. Not only that, but because you're driving those traces across the beachfront, you're not able to use get the same efficiency out of the SerDes, and you're looking about at 12 picojoule per bit all in. Compare this with Passage as the third option. So with Passage, we're taking that GPU, we're stacking it on top. We have less than 5 picojoule per bit all in, including host SerDes, laser, everything. And then you have 400 gigabits per second TX and RX per fiber. This is greater than 2 terabits per second per millimeter bidirectional, And we're only needing about 5 millimeter of substrate expansion for the fiber attached to land on. So this is a sixth of the package growth of 2D CPO and 224 watts of power savings per GPU. Lastly, I want to talk about, the system and application impact. So what is the effect of increasing bandwidth with passage and increasing the scale up pod size? First, I need to provide a little bit of background on expert parallelism and the relationship to scale up. So with expert parallelism, you have multiple experts with independent feed-forward networks. Only a subset of these experts are activated or trained per token, and it's significantly reducing the computational requirements while allowing you to leverage much larger models. There's specialization across these experts as well. On the flip side, you're adding communication. You add a router, and that router activates the K experts. You then need to combine the results of those K experts via an all-to-all operation. As some of the work from Google has shown, more experts leads to better results. And so we're looking at up to 256 experts in our study. This is just an outline of the model parameters that we used to model this. If you want to dig into it deeper, I suggest taking a look at the full paper. But in summary, there's 4.7 trillion total parameters on 32,000 model GPUs. And we have a parallelization of tensor parallel 16, DP of 256, and pipeline parallelism of 8. And importantly, we're exploring 4 configurations of fine-grained expert segmentation. So this is further splitting the experts across those feed-forward networks. We're exploring between 32 and 256 total experts with between 1 and 8 active. In the first study, we're looking at the impact of bandwidth. So we want to say if you have this 512 GPU pod that you've enabled with optics, how much does bandwidth matter? If we go from 32 T per GPU versus 14.4 T per GPU, what's the impact? In both cases, we're having 1.6 T of scale out network bandwidth. And you can see here that just adding the bandwidth is going to buy you about 1.38x increase in training throughput. So we're able to train significantly faster just by providing that extra bandwidth that Passage can do. In the second configuration, we're looking more at the impact of the pod size. So we're comparing pods of 144 GPUs, where each one of those pods is entirely connected electrically. This would be what you expect to see in 2027, perhaps. Each one of these GPUs has 14.4 T of bandwidth, and the scale out bandwidth is 1.6 T per GPU. That would be on the right here. So effectively, if one of these pods, one of the GPUs in a pod here wants to talk to another one, it's going to have to go across the scale out network. In the case of Passage, we're showing a 512 GPU pod with 3D CPO. So it's 512 active GPUs. You have an optical bandwidth of 32 T per GPU and 1.6 T per GPU of scale out. So if there's communication between the different GPUs in this 512 pod, it's happening over optics at 32 T. And this is where you really see a drastic difference in the time to train and the increase in throughput. So for config 4, on the far right, we're seeing up to a 2.7x increase in throughput or decrease in time to train. And the reason for that is because as you add more experts, the chance of having needing to converge those results across that slower scale out domain increases. And so you're really able to leverage the advantage of a larger scale up pod at much higher bandwidth passage. So I want to get to some of the conclusions here. I also want to plug Darius's talk at Hot Chips. This is Passage M1000, 3D photonic interposer for AI. You can see at 10 a.m. PST, August 26th. But in conclusion, what we show in this paper is that increasing the scale-up domain and the bandwidth are critical for continued training improvements. And Passage really addresses the key challenges for next-gen scale-up. And these are bandwidth density, reduced package growth, power efficiency, and the optical reach for 1,000 GPU pods. And in this pictures, we got different visuals of the M1000. We have cut-throughs showing the TSVs and chip-on-wafer assembly. The other images are 16 lambda per fiber guide laser. And then we have our M1000 chassis with 256 fiber attached, the laser and all the cooling put together. So with that, happy to take any questions. I know I'm a bit early, but leave some time for questions.
Thank you very much, Tyler. Excellent talk. The preferred way to ask your questions would be through the Slack channel. And that way I can either repeat them here or Tyler can respond to them via text later at his pleasure. But if there are any questions now, we have a few minutes to entertain them.
So I see one about what is your package size estimated? Is this the GPU referring to the GPU package size? Like how did I estimate that? If that's the case, we're assuming 16 stacks of HBM and 4 full reticles. And see, I see Bob Land says it looks like we've changed from an electrical shoreline to optical shoreline, but the trick is each fiber, and I guess cross chip waveguide can handle multiple wavelengths. Yeah. So I work for Nick, so he says this is similar to what Nick Harris was talking about. So yeah, I hope so. But also indeed, yeah, we're able to get this parallelism of multi-lambda where the electrical trace is only sending one SerDes. We're able to basically fit a lot more SerDes signals onto that optical. And then it says from Norio, using not parameters, but the area entirely requires a novel architecture and block layouts to a GPU on Passage. Is there any practical plans to develop such GPUs in-house or customers? Yes, there is. I don't know how much more I can say there, but yes. Well, I don't see any other questions. Happy to take any other questions on Slack though, if they come up. And again, I want to thank everyone for their time and thank Hot Interconnects for hosting.